Hello and welcome to an introduction to secure product lifecycle management. I'm Beningo and I'm going to be your speaker for today's session. Now, before we dive in and start to talk about secure lifecycle management, let me give you just a quick background about myself. My name is Beningo. I'm the president of Beningo Embedded Group. I've been an embedded software developer now for well over 15 years. I am an independent consultant and I specialize in the design of real-time microcontroller-based embedded software. Now, I've also published a couple of books, one on reusable firmware development and also one recently on MicroPython projects. I also do a lot of writing and content development, very similar to this webinar here that we're going to be talking about secure product lifecycle here. So I write for Design News, which is focused mostly, again, around embedded system design techniques and challenges. So kind of with that in mind, if you want to learn a little bit more about myself, you can always feel free to jump on my website at www.beningo.com. And today's webinar, I'm also putting together in collaboration with SEGGER. And you can also check out their website at SEGGER.com. Now, in today's webinar, what we're going to do is we're going to really try to get you an understanding of what the secure product lifecycle really looks like and how you can go about managing it. So what I'm going to do is I'm going to give you a little bit of an introduction to start off here about what secure products are, why we care about them, what it is that what we need to watch out for. A lot of us attending are probably embedded software engineers, and while we're really good at understanding the details of how to put together a product in general, the IoT is throwing a big kink into things in that we always have to make sure that we're secure. There's people out there who are trying to hack our devices, steal our intellectual property, take control even remotely of our devices, or do things, steal our customers' data or even our data. So we need to make sure that we secure our device. And while there's a lot of focus around device security and application security, security has to extend not just to the device itself, but to the entire management of that device throughout its entire life cycle, from the moment we think up the idea to the moment that that device is retired in the field. So we're going to be talking about what that actually looks like today. We're going to cover, for the most part, focus in on just three main stages, which are going to be development, production, and maintenance of the device. And I'm even going to throw in here at the towards the end, we're going to look at a demonstration of how we can pull together everything that we've been talking about during today's webinar. And I will show you an example of an over-the-air update using mLoad software from SEGGER. And then, of course, I am a big fan of best practices and tips and tricks. So what I'm going to try to then do is kind of summarize everything at the very end by leaving you guys with 10 best practices for managing your secure product lifecycle management. Okay, so with that in mind, let's dive in here now and talk a little bit about why secure product lifecycle management. And when we think about, as I mentioned, kind of secure products, developers are facing, several challenges on multiple fronts, in all honesty. But at least for today, kind of the core ones that we're concerned with is securing our devices and keeping them secure throughout the whole life cycle of the product. Now, a lot of times clients of mine, which tend to be, embedded software developers, things like that, companies building IoT devices, security can be expensive, right? We all have this concept of security. If you go out and you want to build security into your product, we think it's going to be expensive right off the bat. Oh man, I have to secure this device. Oh, that sounds expensive. And it can be, depending on how you go about doing it. And some of the things I'm going to try to show you throughout today's webinar is that there are things we can do to keep that cost well under control, to be completely honest. So we have this conception that security is expensive. IoT security can be difficult to manage, especially when we start to scale it sometimes. Security specialists, again, are expensive, and they are in short supply, which makes it sometimes harder for smaller businesses and startups to really get started developing secure products. And one of the big challenges is that security landscape is ever evolving. There's always new vulnerabilities that are continuously emerging, new attacks. It's like playing a constant game of chess. Even though we're just trying to develop a product and get it out and provide value to our end clients, we have to constantly be also playing the defensive and trying to protect our devices and our clients' data at the end of the day. And, one of the final challenges that we are facing here is teams and developers don't necessarily understand the secure product lifecycle management. So we're going to dive in. I'm going to explain the entire process, at least at a 30,000 foot view. I'll dive a little bit deeper in areas where I can. Again, we have a little bit less than an hour today to discuss these topics. but you should be able to walk away here with a decent understanding of the entire process, see some examples, and also I'm going to provide you with example pieces of software that I use as well that can help alleviate the expensiveness of having to have security experts and having to go through a lot of extra development process and developing software that maybe you just don't know how to do right now. Okay, so let's take a look here before we dive into all of those details. What does the secure product lifecycle management look like? So let's walk through from the very beginning of when we have an idea to launching the product to actually finally retiring that product. So the very first thing that we do when we start to develop a product or we have an idea for a secure product, something that's internet connected, we need to go through and we need to analyze what it is we're building. And when I'm talking about analyze here, I'm talking about kind of going through and doing a threats-based security analysis. I know many of you have probably attended some of my other webinars. I've recently been talking about security quite a bit. This is kind of the third webinar in a series here that I've been talking about different areas around security. And one of those was focused on threat-based security analysis. And it's really important that we look at our device. We said security can be expensive. Well, security is a very vague idea to a lot of people. And what we really do is when we say we need to secure our device, we need to identify what that secureness actually means. So that can be as simple as saying I just need to lock down my firmware, or it could be as simple as saying I need something that even the government would be jealous of from a security standpoint. But the fact is we need to analyze our device, and then we need to basically look at the assets, our data assets. What data is it that we need to protect? At the end of the day, what do we need to protect? And what roadblocks do we want to put in place to protect that data? How are we going to go about protecting it? And we may not need, NSA level protection on our system here. National Security Agency here in the U.S., in case you're not familiar with that, but the idea here is we want to analyze and figure out what level of security do we actually need. If I'm building a kid's toy that's connected to the internet, maybe I don't need to have that extreme high level, but I still need to figure out what data assets or controls are important on the device that I want to make sure I try to protect. So we go through and we analyze. Once I know what it is that I want to protect, I can actually architect my system successfully. This is going to involve me going out and selecting the correct microcontroller that meets my security requirements. So the end of that analysis phase should be requirements for security and for the hardware and software that I'll need in my system. I can also then, like I said in the stage 2, I architect it. So I try to figure out here, okay, how am I going to break up secure software and non-secure software? I want to be able to isolate these. So a lot of times I'll try to, you'll set up, and a lot of security experts will tell you, well, you get security through isolation. So we want to isolate different regions of hardware. We want to isolate different regions of software and get, the kind of create an onion to some degree, where if a hacker is able to get to the outside of our onion, they peel back a layer and discover, oh, I'm in, but I don't have access to anything. And they have to continuously peel through different layers of security and software in order to get to the asset that it is that they're looking to get to. So we go through and we architect the system. This can often also involve starting to select different components that we might be using. So for example, in today's webinar, I'm going to show you an example of how to use mload, which is a bootloader that we can use to securely update our firmware. So you might, at the architect stage, you might start to think about different components that you're going to need. You might just start thinking about which security algorithms you're going to use. Do you need compression? Do you not need compression? How are you going to communicate? How are you going to secure the production? You start to think about some of these things in the architectural stage. And the sooner you can think through some of these pieces and start to even deploy them during your development cycle, the more familiar and the better the odds are that you'll end up with a good secure solution. Now, we also have here, as I mentioned, this third step is the develop and test. This is the area that us developers are most familiar with, right? We're used to developing our software. We're used to testing it. We're used to living in that development environment. But once we have developed it, this is where we start to move kind of a little bit outside of our normal scope here, is moving into production. And that production level needs to be secure. We need to be able to securely put our firmware onto a device and make sure that no one can steal that IP or that we're not building extra units and things like that. And I'm going to talk here in just a minute. We are going to go into detail a lot. This is our 30,000 foot view. We'll go into a lot more detail on some of these here in just a little bit. Once we produce the device, we need to be able to provision it at the factory. So we want to be able to make sure that we can go through and configure the root of trust on the device, read out its unique ID, input some certificates on there, our signatures at the factory itself. basically carrying on a root of trust throughout the entire development lifecycle process here. We then have the ability, we need to be able to commission the device. And when we go through and commission the device, basically what we're talking about is putting in the, configuring the network credentials that will be used for it to go through and connect to the internet and to secure servers. We then have a stage here where we onboard the device. So the device actually connects to a bootstrapping service to get registration credentials. This is going to be where we probably have already deployed it in the field. The end customer has it. They input their credentials onto the device. It kind of enters into a regular use or operational mode. At this point, the user is using the device. It's out in the field. It's connected to the internet. Really cool things are happening. Values being provided to the end customer. During regular use, us developers, we also then enter into the maintenance phase of our development cycle. And this is going to involve us developing new software, pushing that software up to some type of secure server that can then push and propagate the new firmware down into the devices that are deployed in the field, allow them to validate that firmware and update their firmware in the field with new features or bug fixes or whatever it is that they need. And then after some period of time, at some point, these devices are going to reach a point where they're end of life. And at that point, they're going to go and enter into a retirement phase. And that retirement phase needs to be thought through as well, because if you think about it, these devices are going to have data on them. So when I go to get rid of my device, just like what you might have with like a cell phone, for example, you don't want to just take that device and chuck it in the garbage or throw it to the recycling people without ever scrubbing it of data or anything that could have private data on it. So you have to think through, even back here in stage one where we're analyzing the device, we need to be thinking about this retirement phase. How are we going to decommission these devices? What the data we were trying to protect that's on there, how are we getting rid of it? And then how do we put the device into a state where then it moves into a retirement and can't be used anymore? Now, I've just talked about quite a bit. Now, depending on how familiar you are with this process, you may be saying, wow, maybe your mind is blown, or maybe you're saying, I'm familiar with this. Let's dive into some deeper details. Well, in today's webinar, we're basically going to look at this big 10-step process, but we're going to break it down into just 3 main stages that us developers are probably a little bit more concerned with here. We're going to focus in on stage 1, which is going to be the development phase. This is where we're going to be looking at using some type of IDE to develop our firmware, to get ourselves a bootloader. We're going to push that then through a programming device, something like a J-Link or a J-Trace, into our final, into our development boards, into our test products. Once we go through and we develop our initial system and we're happy with the way that looks, and we're getting ready to deploy it in the field, what we do is we push that from our development environment, which might be something like Embedded Studio. We actually push that up to a secure firmware server that also acts as an authentication server. So basically, I can push from my development environment, I can push up to a server that's going to run. It will say, hey, here's the new firmware. Okay, yes, this came from the manufacturer. I can verify the signatures and the certificates, and I can do a hash on it and verify that this thing hasn't been modified. So I can accept then the new firmware. At that point, then this firmware that we push up can then be deployed to like a flashing tool that is used by the manufacturer to actually go out and provision and commission the end product that will be sold. But at this point, it's still at the manufacturer's facility. Now, you can see here there is a line here that's kind of being drawn across here from development into test and production. The idea here is that the sooner we start following a process like a secure product lifecycle management process, we can test out and ensure that the servers are working the way we want them to, that our maintenance cycle will work the way we want, because we can develop, we can deploy through this process to test our device on the benchtop and get very familiar with it, get very comfortable with it. And then at some point we say, okay, now we actually go into real production. And then, as that cycle goes, we move into a, second stage is this test and production. Third stage is going to be where we basically perform maintenance. So for maintenance, we're really continuing development incrementally, adding new features, fixing any bugs that are discovered in the field. And then we are also going to perform in-field firmware updates. And there's several different ways that can be done. Showing how this process generally works. As you can see here, we're going to use the firmware server, push it through the web down to the devices, and it could be that we use something like mload, which is a firmware bootloader. It goes out, talks to the server, says, hey, is there an update? Yes, there is. It pulls the data back down then and performs a firmware update. I'll show you here a demonstration of how that actually works here very shortly. Or it could be that you have field personnel out in the field. You can download into like a portable flasher tool, and then you can manually perform the updates if you're working with a device that isn't going to be internet connected. So these are going to be the 3 stages here that we want to take a look at in a lot more detail. Okay, so let's dive in and start looking at the first stage. Now, the first stage of SPLM is going to be development. So this is where we're going to go through and we're going to have some type of development process that we have to follow. Now, the process here that I like to follow, typically when I design a device, ARM has put together a platform security architecture process, basically. And it's broken up into 4 main stages. In the first stage, this is for when we're starting our device, just like I mentioned in the 10-step process here. So we're going to go through and we're going to analyze what it is that we're building. We're going to try to identify, what are the important assets? How could those assets be attacked? What are the potential threats to my device? We're going to go through and perform an analysis. So that's stage 1 during development. The next stage is where I go through and I architect my system. And when I architect it, I'm going to try to partition it. I'm going to try to create a hardware-based root of trust. I'm going to identify chips that I can do that with. I'm going to try to figure out how I can parse out my software into secure and non-secure components. I'm going to go through and I'm going to identify critical components that I want to make sure I have in my system. So for example, I'm going to need cryptographic engines. I'm going to need a secure bootloader. I'm going to need to make sure that I have the ability to compress software potentially or decompress it. I'm going to need to make sure that I have connectivity libraries, things like USB, Wi-Fi, and so on and so forth. So we're going to discover that there's several different types of libraries we need. We're going to want to try to figure those out as we're architecting our system. And then finally, once we go through and we do architect them, we can finally move into stage 3, which is where we're going to implement it. So this is where I'm going to go out into the field. I may go and try to, one of the best things we can do is actually try to leverage existing code. And leveraging existing code helps save us from having to learn how to develop it ourselves, for one. But 2, it goes way more than just us, saving us time. It's the fact that, software that's already been developed and that's out in the field, it's proven, it's well tested, it's usually maintained in a really good manner, provided we select the right tools. You know what I mean? So in order to help save ourselves, one of the things I always do, I have a product I'm developing. I want to focus on the application. I want to focus on the value that I provide to the end customer. So I don't want to go and build my own TCP stack. I don't want to build my own compression algorithms. I don't really want to build my own bootloader. I used to build bootloaders all the time. It was one of my, I thought were one of the fun projects to actually go through and develop. But, over time, there's so many different resources out there. For example, like SEGGER's mload, that it just makes sense a lot of times to go out and just get the software and it's pre-integrated, then you can focus on your application code. So with that in mind, that's stage 3. And then if you want to, you can also get your product certified. So stage 4 is where you can go through and get your product certified for security. And all that's basically doing is it lets you tell your end customer that, yes, I went through this process of analyzing, looking at my threat models, architecting, and then implementing my software. So this becomes a 4th way to kind of show your customers that, yes, I was thinking about security from the very inception of this device all the way to the time when I went into production. Okay, so that's a process that we want to follow. Another thing that we want to make sure that we're doing, as I kind of mentioned, this is actually really critical to a lot of secure devices. We need to make sure that we partition our system appropriately during development. So kind of almost going back to that architecture standpoint, we want to make sure that we select microcontrollers that can support hardware-based root of trust. We want to make sure that we can partition non-secure processing elements in one area of the processor, that we can have secure processing environment in another. Within the secure processing environment, we may even partition. You can see here, we might partition this up into several different areas where we have a trusted partition. We may have secure apps that are running in there. We want to think through that in the architectural stage. And I mention this because I see a lot of companies and teams that try to put security as the last thing they do. They try to develop their product, and then they say, a month or 2 before they actually go to production, they say, all right, let's lock this thing down and make it secure. You can't do that. It's kind of like, you can't build quality in at the end of a development cycle. You have to follow it throughout the entire thing. So with security, we really do need to be, from the very beginning, looking at how are we going to secure the device? What are the assets? What tools am I going to use in order to ensure that I can maintain this process throughout the entire development lifecycle? I see people select microcontrollers all the time that don't support security capabilities, hardware-based roots of trust, even unique IDs, which are very important during the secure product lifecycle management, like during the production stage. So really, take the time and make sure that you properly partition and select the right parts for your device. And, it's going to spawn from there further into having the right tools. Okay, so when we start to look here at stage one, so we're talking about analyzing, we're architecting what it is that we're building. We need to go through and, what's one of the major pieces for the security standpoint for this stage of the development lifecycle is to make sure that you have secure firmware and that you have secure bootloader and that you've prepared a bootloader to work with your system. Now, a lot of times I see companies wait till the very end, again, on bootloaders. They develop everything else and they say, hey, now let's go find a secure bootloader. You should go out right in the beginning of implementation and get a secure bootloader right off the bat. And the reason for that is you want to get that early so that you get familiar with it, so that you can build it into your actual development processes. There's no reason you should develop in process A during development and then process B during maintenance. It should be one consistent development cycle. So what we want to do here during this stage is we do want to go out, we want to find the right tools that we can use. Some of the tools that I use, for example, I use SEGGER's Embedded Studio. We can use a bootloader, we can develop our firmware, we can actually compile it, we can create our firmware image. For years, I've been using the J-Link Ultra Plus and also the J-Trace. These are a couple of development tools that I've found to be absolutely critical when I develop software. I used to go out and always buy the cheapest, the absolute cheapest debugger I could. And it always worked with just it was like always those onboard debuggers that weren't very capable. And one day I went out and I bought a J-Link Ultra Plus, and it just blew my mind on the difference in speed, the ability to have unlimited flash breakpoints, and more and more as you work with maybe safety critical devices, or you need to work with secure devices, or kind of validate your firmware better. I've moved from using something like the J-Link Ultra Plus into using more of a J-Trace. And the reason for that is that just the ETM capabilities of that device. So it allows you to be able to trace, do instruction tracing, to see the details a lot more. It allows me then to visualize what the application's doing. I work a lot in high reliability software, I'll call it, or quality software. I'm working on things maybe in defense industry or medical devices. Working on small satellite flight software. These are things that these things can't fail, or maybe they're networks of IoT devices, and they're remote in such a way that you can't go out and physically get your hands on them. So the code has to work. And I found that being able to use these tools, that they integrate very well together, and it allows me then to very easily go through and develop my software. And once the software is actually developed, as I kind of mentioned before, within Embedded Studio, if you use SEGGER's firmware server and authentication server as well, you can actually, once you compile the code, you can actually push your firmware from Embedded Studio, from your repository, up into this authentication server and the firmware server, which then makes it easier for you to deploy it for testing and also for the production lifecycle as well, or later on maintaining your system. So these are a couple of things that I do. So what else do we want to do during the development stage? Well, I need to make sure I develop or identify a secure bootloader for firmware updates. Now, bootloaders, like I said, I used to do this all the time from scratch. I don't do that anymore. There's lots of other tools out there like mload that I can use. It saves me from having to go through the hassle of creating a bootloader and maintaining it and ensuring that it's secure. Instead, I can rely, for example, on SEGGER to go through and maintain and provide that bootloader for me. Saves me lots of time in my development cycle. I want to make sure that I prepare my firmware image. I need to go through and actually, once I create this, I need to validate it. So I need to push this thing. It gets validated that this is going to be the device for this particular product. I need to think through fallback processes. So when I'm thinking about bootloaders themselves, do I allow a fallback process? If I try to do a firmware update and it fails, how do I handle that? Do I just fall back? Do I require a new firmware version? In order to keep your device secure, a lot of times many modern products don't allow you to actually fall back. They look at that as a potential attack. Because if I can go to a device and say, hey, you're running firmware 1.3, I know that 1.2 had a really cool exploit that I want to use. If I can force that device to go back and fall back, to update into version 1.2, then I can exploit that attack. So a lot of times in these bootloaders, you build in it, you decide what your fallback process is going to be. Do we only allow, once I get to 1.3, I can only accept 1.4 version of firmware. And it's got to be, of course, signed and certified, so that you have to know the proper keys in order to be able to put those devices on there. So that ends up being a critical thing to think through is this fallback process. We also need to think through encryption. How am I going to encrypt the image? Okay, if I'm going to encrypt the image, how do I decrypt it? What algorithm do I use to encrypt it? I got to think through these things as well. Do I compress it? Firmware images, they used to be really tiny. I mean, the first microcontroller I ever worked on was a PIC16F84. It had 1.7 kilobytes of flash space. Very tiny. But a lot of modern processors today, even in the microcontroller world, you can be looking at 2 megabytes worth of code space. So while, with internet speeds that may not be a big deal, if you have a server and you're pushing stuff out over maybe a cellular connection where every byte matters, you get charged for every byte of data you push out there, and you have tens of thousands or hundreds of thousands of devices out there, man, that could get really expensive. It could use up a lot of bandwidth. So you want to make sure that you can also compress your image, transfer it, decompress it, decrypt it. This starts to be a lot as you start to think about this. Then we have to authenticate the image. I need to decompress it, authenticate it, et cetera, et cetera. And of course, I need to make sure that my firmware is able to do that. Now, to be completely honest, this is why a lot of teams that I encounter, when they start to look at all these things, they just say, this is too much. It's going to cost me too much. It's going to be too much time. Does my product really need this? And the fact is, a lot of times they do, but people try to cut corners on security because they think it'll save them costs and money. But the fact of the matter is a lot of these tools, are already exist, and you can get them for much less than it would cost for you to develop them in-house at all. So let's take a look at some of the things that we can do. So, talking about during development, all these, different things I was just talking about, encryption, compression, and, what tools do we need to make sure that these things actually happen. So one of the things that, one of the reasons I partnered with SEGGER for this webinar is that they actually provide a lot of these software tools and hardware tools that you need for secure product lifecycle management. So I'm going to go through some of these things really quickly right now. So for example, we talked about needing some type of development environment. You could use something like Embedded Studio, which just enables efficient development for embedded devices. So, you can program devices that are Cortex-M, program things that are Cortex-A as well, along with a wide other range of architectures. But the nice thing is that, again, it's a nice integrated development environment that can integrate with the server that they provide, that can easily integrate with other software libraries as well. Makes it pretty simple. As I mentioned, we might need to compress our devices, or our actual firmware, when we're going to go and deploy it. So you might use something like mcompress, which is going to be just a way to compress static data to be linked into an application, and then you can actually decompress it on the target. So this ends up being areas where we can push static data, static code that we want to run on our system. So as part of maybe a firmware update, for example. Now, of course, when I go through and I'm designing my bootloader and I'm architecting my system, I can think through which pieces of the puzzle I actually want or need. So I don't necessarily need to go through and say I need, if I need everything, I can go and, get everything. Or I can just say, well, I really like to be able to compress my data. Maybe I go out and get compression, and then maybe I just want encryption, and that's good enough. You can kind of pick and choose based on what your actual needs are. There's also a software library called mSecure, which is basically just a software solution for securely authenticating digital assets. So we can use this to help secure our products in order to try to decrease the cost of protecting our devices. So it provides several libraries here for us to be able to easily protect our devices to help prevent cloning and hacking. So that ends up being kind of an interesting, useful solution for us here. It also does other things. It has different algorithms to be able to fit in different size environments based on how we want to secure the system. Which makes it pretty useful, I think, for us as developers. Then I mentioned there's also mcrypt, which is for us to be able to encrypt and decrypt our our binary images or even our communication channels. There's things like this library is actually NIST validated, so it very high standard, and it just provides essential cryptographic algorithms that you need in order, AES encryption 256, things like that you need in order to be able to encrypt your images successfully. So a couple of other tools that I'll just mention here, and this is going to be one that I'm going to show later, and the reason for that is that the mload is a bootloader. We can do over-the-air updates. We can do updates over USB or SD card, or through a flash programmer. We can kind of adapt and adjust this bootloader based on what our needs are. So we can use the mcompress, we can use msecure, we can use mcrypt in order to have really secure devices that are encrypted, compressed images, and so on and so forth. And it kind of all integrates together. So in a little bit, I'll show you how that actually works from a standpoint, but I want to look at it as part of the maintenance development cycle. Okay, so as we start to look at these different tools, and we're looking at a development cycle where we say, hey, I need mload on my device for a bootloader. I'm going to use mcompress to be able to efficiently transfer these things over the wire, so I don't have to pay tons of fees maybe for internet access or whatever it is, depending on what device it is you're working with. So I stop and I take a look at this, and now I say, okay, time to test and manufacture the device. And you might say, well, testing and manufacturing, what are the real threats to my firmware? There's not really any threats. Well, if you were thinking that, you'd actually be wrong. There's 4 main threats that we can really see for our devices during production. The first one is that if I don't secure my device, I could actually have someone get a hold of my image, and then they can take that image, they can run it through a tool that will basically put it back into C code, and I can start to reverse engineer what your secret sauce for your device is. So I can go and look at the device, I can reverse engineer it really easily, and then I can use that code to leverage to accelerate my own competitive product to compete with you. And that's something obviously you don't want. So this is why we need to very carefully think about the secure production cycle. The second thing that we need to be concerned with is firmware modification. If I can get a hold of your firmware and pull it out of your device, or if I can pull it off of a server somewhere and it's not encrypted and I'm able to just get access to it, I can go in there and I can make modifications to it. And I can then make those modifications so that I can either watch data coming on, or maybe it allows me to steal some type of intellectual property or some privacy data or something that's worth, something that's valuable to me as a hacker. So maybe it's just that I want to be able to push back malware to the device and take control of it and use it in a botnet or something like that. Who knows? But the idea is we don't want people to be able to modify our firmware and deploy it to devices either. The third thing we don't want to do is we don't want loading of unauthorized firmware. So we can have people who modify the firmware, but we also don't want them to be able to load that firmware back on. So we need to be able to protect it using keys and things like that. And we also, on top of that, we want to make sure that we're not able to deploy our firmware on unauthorized devices. You've probably heard of situations where, someone has a manufacturer, they're running 2 shifts, shift 1 and 2 comes in, they produce a device for them, they're shipping them out to the customers, everything is awesome. And then, those first 2 shifts go home, shift 3 comes in, the midnight shift, and they're producing the product. It's just not for you. It's for themselves. It's for the manufacturer who's basically cloning your product using your firmware, your electrical hardware, and then they're selling it somewhere, in a different country, or maybe even directly competing with you just by, changing the enclosure and putting a different different sticker on the front or something. We don't want those types of things to happen. So those are the types of things that we want to protect against. And when we start to think about those types of things, this is where we need to make sure that, for example, we have security tokens that can be stored on the actual device. So let's dive in here and talk a little bit about how this can work. So when I go into testing manufacturing, I want to make sure I have a unique ID on my device. My device, the actual microcontroller, has to have a unique ID. That unique ID can then be used to generate security tokens that can, one, be stored on the device, but then tools like Flash or Secure, so that they can go through and use that physical ID and then generate, say, hey, this is the ID. Let me validate that ID with the authentication server. Okay, this is good. Let me generate some security tokens and public-private keys and such in order to be able to basically provision at the factory that device. And what that does is it then allows us to inject and kind of say, hey, this is our device. We're going to essentially what we're doing here is we're setting up a root of trust. We want to set up a root of trust that says from the moment that the microcontroller leaves the manufacturing facility of the microcontroller vendor, we want to make sure that that there's a key on there that says, hey, this is, for example, this is Cypress's microcontroller. And then when I get that part as, the developer or the company who's building the product, I want to be able to take that thing and say, hey, look, there's a root of trust. Let me use that key. Let me use the unique ID of the device. Let me run that through Flash or Secure. Let me get that to my firmware server and authenticate that. Okay, yep, this is the device. It's not, it has a unique ID. Let me use that ID then to generate my security tokens. Let me go back now and provision that device with Flash or Secure and actually put my security tokens on there. Now only I will be able to push firmware on there. So then I can push my secure bootloader on there. I can push my secure firmware. I can push my application code. All of that can go on there. But the security tokens, this root of trust, you don't have a secure production cycle or development cycle without having those security tokens. It's absolutely critical. And one of the tools that we use for that, like I mentioned before, is Flash or Secure. And it's basically just a one-step solution that can query a trusted service. It can install a root of trust as part of your production process, as opposed to having to do other, multi-step processes where you have third parties involved and you have to prepare and kind of do all kinds of interesting things. And there's an opportunity for that process then to be interrupted and for someone else to inject their own security keys. So you want to make sure that you do this from the very beginning. And basically what we're doing here, as you can see on the slide, we start here with the server. We're going to push it to our device. We use Flash or Secure here. It programs and verifies the device. We were basically creating a hardware authentication process. We're programming our bootloader. We can do hardware test and verification as well, and we can install our initial version of our firmware that will be used when we actually go out into the field. Okay. Now, as I mentioned before here, I kind of mentioned a process that's followed. Well, here's kind of a little bit of a better visualization of what's actually happening here. So what you can see here is we have a device where we read the user ID. From the device, it goes into Flash or Secure. Flash or Secure then sends a unique ID up to a validation server. It validates it, creates a signature and a key, which is then sent back over the internet. Then using the public key, Flash or Secure is able to validate this and then actually program it into the microcontroller, at which point then we can include the firmware and no one will then be able to go in and change anything on that device without having the proper credentials. So pretty neat process, useful, very useful tool. Now the third stage here, once we go through and we produce this device, we put our initial firmware on there, we've got the bootloader on there, we're looking pretty good here. But there's still a third phase, right? A third stage, and that's this maintenance stage. And this is where we continue development as developers, but we also have to now worry about servicing the device in the field. And that servicing can be to fix bugs, but hopefully it's just to continue to enhance the product and add new features. So how do we go through and update the firmware in the field? Well, there's two different ways. We can push it through the web directly to the device, have a tool like mload that'll sit there and pull the data. We can do that with over-the-air updates. We could do that with, you walk in with a USB stick and stick it in the USB drive if you want, where you maybe use something like a USB device protocol. We could use an SD card, Wi-Fi, Ethernet. Pick your favorite peripheral. The fact is you can select and kind of tune mload, the secure bootloader, however you want to be able to work for the device and for your particular deployment. And you can see here in this, we're pushing the firmware down. It's secured and encrypted. This here is just kind of showing that it's compressed. It goes into the mload. It would decompress it, deploy it on the device. In some situations, though, you don't have the ability to push. Not every device is IoT. There's still devices where maybe you have a physical maintenance person that goes to see the device. Well, in that type of case, you could push the secure firmware to a tool that's like a portable flash tool. So Flash or Portable is a tool where you can then push your secure firmware onto the device. It's controlled and maintained. You go to the device and you can do a secure firmware update locally while you're right at the device. So that can be again a useful way to go about doing this as a developer. Now, I'm talking about a lot of things. So how do we pull all these pieces together? Well, again, to give you an idea here, and this is going to lead up to this over-the-air update that I'm going to demonstrate to you here. There's lots of different software components that may come into play here in maintenance and the firmware update process. So, for example, I might want to use, if I'm using Ethernet, for example, or Wi-Fi, I might have an Ethernet stack like MNet that I can use for internet protocol stacks. I might have mFile if I want to have a fail-safe file system for my embedded system, which is really important. A lot of developers don't understand, how difficult it is to actually have a file system that won't corrupt itself. A lot of people will go and use a generic open source file system and just be like, oh yeah, hey, cool, I have a fat file system now. But you get a power glitch or something goes wrong on the system, and it's really easy to just have that system fail, and then you lose all your data that you had on there. So you can use something like mFile that is safe and secure, and it's file safe and optimized to run on an embedded system. But more importantly, we can also use it to interact with an SD card and store data and retrieve data and store our firmware update if we want. So we can actually over Wi-Fi use Wi-Fi support, get that into our system, and then we can go through and store it on an SD card and then perform an SD card update, for example. Or as I mentioned, we might have a USB drive that we're going to go stick into the device. If that's the case, I might use something like MUSB device in order to act as a device to update it. Maybe I actually have a tool I plug in and I want to, on my tablet, push it over to it. Or I might use something like MUSB host if I wanted to. If I'm doing it over the internet, I'm going to be using MQTT, which is very popular. If I'm going to connect to a cloud service provider, a lot of those communications is all done over MQTT. So we might use MQTT in order to make sure that we're able to successfully use the message queue telemetry transport protocol in our software. And then, as I mentioned before, there's this Flasher portable tool that's just a standalone in-circuit programmer that you can set up with a firmware update that doesn't even require a PC to be present. So you can just go plug into the device and update your firmware. And again, following, assuming that you have the right credentials and all of these types of things. Okay, so I've talked quite a bit now about the three different stages, right? Let's look at an example of how we would actually maintain a device in the field using mLoad. So what I'm going to do now is I'm going to show you how we can actually go through and do a little demonstration of using mLoad to update firmware. The example that we're going to be looking at here for the demonstration, as I mentioned, is going to be using mLoad to perform a remote firmware update. And this particular example it's just on this development kit that you can see here in front of us, but it's supposed to simulate an elevator control unit that we're going to update remotely. To give you a quick look around this, you can see here we've got a Wi-Fi module right here. We've got an LCD screen, which is going to give us the status of the application and the firmware update as well from mLoad. Up here we have a USB connector, which I'm going to use to actually power the device. And then over here we have Ethernet, and then we have some LEDs that will show us kind of the status of the firmware update process as well. Over here you can see that there's a micro SD card slot, which is where the firmware is going to be downloaded to, and then once it's validated by mLoad, it's going to then be validated and then flashed into the microcontroller, which you can see just right here in the center of this development board. There's some other features of this development board, but at least for today's demonstration, they don't really matter. So again, what's going to happen here is I'm going to power the board up. It's going to go through, it's going to initialize, it's going to go and check for new firmware. When it finds it, it's going to say, hey, there's new firmware. It's going to download it. It's going to reset, go through the update process. We'll see the progress of the update, and then we'll see that the firmware gets updated. So let's now, with that kind of quick overview, let's actually go through and run the demo, and I'll explain what's happening as it actually occurs. All right, so as you can see here, I've got my embedded system powered up. It has an IP address, and now it's going out to check for an update from the server. Now, it's actually contacted the server, and we can see here that, hey, it found a new update. So what it's going to do now is it's actually going to go through and it's going to load the update. So it's downloading the update, storing it on the SD card. It's now successfully downloaded it, and what's going to happen here is it's going to restart the device, and on startup, the mLoad bootloader is going to check that SD card, notice that, hey, there's new firmware here. Let me authenticate it. Let me verify that it's actually from the source I want it to come from. If it is, it's going to say, hey, look, I'm going to update the target. And as you can see here, it decompressed and it's now actually reflashing the device, putting brand new firmware on it. We originally started at version 7.07. We're going through a firmware update here, and we should find now that it's been successful, it's going to reboot. And what we'll find here is it's going to have actually increased the version number here that we had, and we're now at version 8. Now, this is a real simple demo here, so it's going to go through, it's going to get an IP address again, and then what will actually happen is it will then hit the server again. I've actually got more firmware loaded, so it'll actually say, hey, there's actually a version 9.09 that's available, and it would actually go through the entire process again. So this is just a simple demonstration of how you can use the mload over-the-air update server. Okay, so what you can see here is I've got this, behind the scenes here, I've got the server actually up and running. And what we're going to do here is the device is actually going to go out. It's in the process of actually connecting. You can see here it's getting a firmware update. It's downloaded it to itself. And now it would actually go through a firmware update process. So the device is actually right now next to me going through the firmware update process again. But as you can hear there in the background, but I actually want to show you what's going on behind the scenes here. So what's actually happening is you're going to find here that there's this dashboard that we can use. And I'm going to refresh this here because over the last couple of minutes, there have been some updates that have been going on here. And you can see we've got some activities here where we had an update and no active updates going on. But what I could actually do is if I can check in this dashboard to see how many devices are in the process of updating. So if I had connected 2 devices and had them running here in the background, I'd actually see that there were several devices potentially running in the background that are actually updating their firmware. One of the nice things about this as well, from within the dashboard, I can obviously adjust some settings. I can actually come into the demo that I was actually executing here, which is the mload OTA Wi-Fi demo. I can click on here, and this is actually where I can configure the firmware update process. So you can see here I've got a new piece of firmware here, firmware version 9.09i, which is going to be the latest and greatest that it would be updating to. You can see there's actually a firmware revision history here. We had started out at version 7.07G, updated to 8.08, and it is in the process of updating to version 9.09i. I can also, from this dashboard here, also come back here and see in the device list, I can see which devices I actually have connected here. Now, I have this device here that I've been playing with. So you can see here we just made contact just a minute or so ago. And you can see that the version that last updated was version 8.08.08. So this ends up being a very useful way on the server side to be able to actually go through and manage the firmware update process, but also to see what's actually happening during the firmware update process and see how many active connections there are and see what's happening with the device itself. So as we've seen, the main piece of software driving that demonstration was mload. And mload is the bootloader. Basically, what this is allowing us to do is it's allowing us to do firmware updates. And the example was doing over-the-air updates. Now, one of the things that we can do here, the software is validating the firmware images I talked about before. It can work alongside several different other pieces of software. So, for example, if I wanted to ensure that I was doing encrypted updates, then I could use msecure or mcrypt with it in order to get the encryption algorithms. I might be able to use also authenticate using signatures such as ECDSA or RSA, which can also be working alongside and can be integrated into the software package here. We also have the ability, if we want to use a compression algorithm. So compression can be very useful if I'm working on a device that is going to be using bandwidth where I have to pay by the byte or the megabyte of data used, and I might have thousands of devices deployed. Well, I don't want to pay for all that bandwidth if I don't have to, so I can compress my image while I transfer it over whatever the pipeline is I'm going to be using for firmware updates, such as cellular or something like that. So it allows me to very easily do my over-the-air updates. And if we had to, we could configure this to work on more than just, a Wi-Fi module. If we wanted to perform an update over a UART, RS-232 or something like that, we can do that. We just got to make an adjustment to which interface we're expecting to receive the firmware over. We could use, for example, a USB stick, an SD card, or even a simple USB cable. So let's take a look now at what's actually happening behind the scenes with the demo software in a little bit more detail. Now, as I kind of explained a little bit before, but because it was all just kind of visually looking, at the actual firmware update being done, this is what the actual demonstration was showing us here. So you can see here we had our trusted server, which was running. Over Wi-Fi, it would go and check for an update from the firmware actually polls the server to see is there firmware available. If there is, it pulls the firmware down from the trusted server. It saves the update to the SD card. Once the update has been saved, it performs a reset. On startup, the mload then says, hey, is there a firmware update available on that SD card? Yes, there is one. It then goes through and validates it, and then it performs a firmware update if all the signatures and everything match. So you can see here then, during that checking phase here, you can use mload to decrypt. We can use mcrypt to decrypt the image that's stored there, to decompress the module, to go through and validate it, and then we actually use msecure then to authenticate and validate that the firmware update is correct. Then we actually go through and perform the firmware update. So these are kind of those major steps that are performed. Our device is running code. It's running mload. Our actual application code checks for firmware updates. When it finds it, it stores it locally. Then on a restart, mload goes through, it decompresses it, decrypts it, validates it, and then if everything looks good, then we put it in the actual device, and we update ourselves to a new and improved version of the software and let it roll. So that's how that piece works. Okay, so at that point now you should have a pretty good understanding of the main components, that the process that we follow, the 10 steps, the 3 main stages of the secure product lifecycle management. You have an idea of where you can find those different software packages. From SEGGER, they have the ability to kind of pick and choose which components you need. They've all been already tested and integrated together, so it's just basically going and pulling what you need, and then you're off and running with minimal integration efforts, which makes things very useful. Now, before we leave here, though, today, I do want to talk to you a little bit further about best practices. So I just want to leave you with 10 best practices here for the day. Now, the first best practice, make sure that you recognize that producing a secure device goes beyond just secure development. So what I mean by that is it's more than just building a secure application. There's an entire life cycle all the way from the way that you develop the product and analyze it, especially the manufacturing process you use, is going to determine whether the device is secure or not. So you need to make sure that you think about security from the very moment that you start designing your product, and look at all the different areas from development through maintenance and retirement to ensure that you've covered everything and thought through everything from a security standpoint. Best practice 2, make sure you follow PSA guidelines to properly identify your systems threats and to build those requirements for your hardware and what software you'll need. Best practice 3, make sure you select a microcontroller that supports hardware isolation and secure updates. Now, I've seen a lot of people who will select a microcontroller that doesn't support cryptography, or doesn't support root of trust, and it doesn't have kind of these hardware-based capabilities built in that you really should have in order to build a secure solution. So this is why PSA kind of pushes on analyzing and developing your requirements up front for your device and identifying your assets, because you need to be able to identify the right piece of hardware to use. Because with the right hardware, that also then integrates with the right software packages as well. You want to use the right software in order to help accelerate your life, your development cycle, getting your product in the field, and making your life a lot easier as you're designing and deploying these things. So best practice number 4, you do want to identify your contract manufacturer early to develop and test procedures. So you don't really want to be you want to develop your product like you're maintaining it. You want to have that secure product lifecycle built into your development cycle from the very beginning. So make sure that you have identified your contract manufacturer up front. Make sure that they're helping you develop the processes as well, that you're both comfortable with it, that you're going through multiple iterations and cycles of it, and prove that you can successfully follow these processes that keep your device secure. Now, best practice number 5 is to leverage secure tools like Flash or Secure for your product firmware and for device manufacturing. So one of the things that I didn't mention earlier here is that one of the nice things about using something like Flash or Secure is that you can actually limit how many devices you actually program. You can go through and make sure that, if you're building 1,000 devices, you only program 1,000 devices, and that they're not, the midnight shift isn't doing another 10,000 pieces behind your back. It's validating and authenticating every single device that gets programmed. So that allows you then to have that tracking capability as well of what your manufacturer is actually doing. A lot of times we hand our, and I'm not saying most manufacturers are going to, they're there to help you. They're not doing anything shady or behind your back. But we all know that there are occasionally instances where you run into problems like this, and tools like this can help protect your device. But they can also, more importantly, they can set up that secure root of trust that you need on your device in order to be able to successfully have a secure product. It's not just about a secure app. It's about that secure root of trust and maintaining a chain of trust throughout the entire life cycle of your device as you produce it. And Flasher Secure is one of those tools that you can use in that process. Now, best practice number 6, just implement your secure product lifecycle management cycle early so it can be tested throughout the whole development cycle. I've kind of mentioned this already. Best practice 7, leverage existing software solutions for secure bootloading to minimize time to market. There's no reason anymore to reinvent the wheel. A bootloader, we don't need to design our own in-house bootloader. It makes a lot more sense to go out and get one from someone like SEGGER, to get the other pieces and components that we need in order to be able to focus. Like I said, look at your business plan, look at what you do as a developer, and say, where's the value? If the value is not in a bootloader or in a compression algorithm or in authentication or in encryption, go somewhere and get those libraries. Don't spend your time doing that. Someone else has already done that. They've already made it very robust for you. And then that allows you to say, what is it my client needs? They need feature A, B, C, D, E, and F. And go through and actually do that for them. Okay, so leverage existing software. Best practice 8, practice provisioning your devices and becoming familiar with the entire SPLM process. Best practice 9, select solutions that are integrated and tested together to minimize cost and time to market. A lot of companies don't recognize that a major piece of debugging that really slows down development is different software packages that haven't been tested and designed to work together. If you have pieces of software that have already been tested and integrated together, the amount of time you spend debugging is dramatically decreased. So keep that in mind, integrated and fully tested solutions. And then best practice 10, which is a little bit tongue-in-cheek here, is just to explore solutions at SEGGER. On their website at SEGGER.com, they have just an amazing selection of product offerings that kind of help developers accelerate their development lifecycle. And then also you can check out my website at Beningo.com, which is, I do as an independent consultant, I help people with software architectures and doing secure processes and training and things like that. So you may get some ideas from a lot of the free content like this webinar or other blogs or white papers that I put together. Okay, so now that you understand a little bit about the secure product lifecycle management, you've been introduced to it, you know what our goals are, you know what the overview is, where do you go from here? Well, a couple of things, a couple of real useful resources. SEGGER has put together a secure PLM webpage that's really useful. It reiterates some of what we've touched on here, but also provides you links to other useful resources. I will later on send out everybody just a follow-up email that includes these links and also a link to the recording for the webinar. So what you can do is you can see here this link is actually live. You'll be able to just click on the link and go and read that page. So it's SEGGER.com. It's Secure Product Lifecycle Management. I'll send that out to you guys here shortly. You could also sign up for my Embedded Bytes newsletter. I send out a newsletter twice a month that basically just goes through and it shares blogs I've written and tries to connect with people in the industry, whether you're a president of a company, a CTO, or a developer who's down in the dirt trying to actually develop the product, or maybe you're just managing a team of developers. I put articles and things together that try to help all stages of product development. And then there's also a link to my blog there as well. So, all right, I hope that you've enjoyed this introduction to the secure product lifecycle management. I hope you understand now the 3 stages and that you also have some ideas on where you can go in order to get more information and also to help accelerate your own secure product development. So with that in mind, thanks again, and I look forward to talking with you again in the near future. Thanks.